I'm very happy to present Sarath's work today. He will give us a talk about human-aware AI and the foundational framework for human-AI interaction. And he has an impressive academic journey and indeed amazing research, and dedicated 6 years to the PhD, and produces highly influential research that has been featured in esteemed AI conferences such as AAAI, ICAPS, IJCAI, AAMAS, IROS, IRA, ICRA, ICML, ICLR, and as well as the AI journal. His exceptional contributions have garnered over 1,500 citations and solidifying his reputation as a leading expert of the field. So currently, Sarath is an assistant professor at Colorado State University, and his core research interests include designing a human-aware decision-making system and that can generate behaviors that align to human expectations. He also won multiple awards, like the Best System Demo and the Exhibit Award at ICAPS 2020, and Best Paper Award at the Planning and Reinforcement Learning Workshop at the ICAPS 2022. He has also recognized as a AAAI 20 Outstanding Program Committee member and highlighted reviewer at ICLR 2022 and IJCAI 2022, and distinguished PhD member at top reviewer and top reviewer at NeurIPS 2022. So please now join me in warmly welcoming him to this virtual stage.
Thank you so much. Yeah. So as Sylvia mentioned, I want to talk to you guys about human-aware AI. And I'm hoping by the end of the talk, I can convince everyone here that, human-aware AI, at least as I define it, can be a potentially foundational framework to both understanding and designing human-AI interaction. So as Sylvia mentioned, my name is Sarath, and I am an assistant professor at Colorado State University. Okay. To start the talk out with, I want to start with a concept from psychology. It's called double empathy problem, and it's a theory that was introduced to explain the communication issues that autistic people face. So to realize why this is important, you have to understand that the prevailing, like the theory about why autistic people face issues in communication was something called as mind blindness. It was just the fact that at least psychologists used to believe that the only reason there is a communication issue is that autistic people had a hard time ascribing mental state, and that's what the problem was. Okay, but psychology has moved on from that and realized that this is a two-way problem. It's not just that autistic people have a hard time ascribing mental states to neurotypical people, but neurotypical people also have a hard time understanding the cognitive process with respect to an autistic person. So it's a two-way problem. Okay, and I want to make a claim in this talk that there is a double empathy problem that exists between humans and AI. So it's not just that most existing, AI systems are incapable of doing things like mental modeling and things like that. People naturally have a bad time ascribing mental state. Most of the time, they anthropomorphize these systems, and that could be, result in a lot of, completely bad outcomes and things like that. And this double empathy problem in the context of human AI interaction is much worse than the ones that we've seen in between autistic and not neurotypical people. Okay, so obviously, one of the questions you might raise, ask is, why do we care? No, we are living in proverbially a golden age of AI. At least every day, if you open New York Times, there's one article or the other about how AI did X or Y or Z. The thing I want to kind of focus on is like how many of those applications you see are being applied in safety critical or mission critical settings. Settings where the stakes are more than just whether you would get a bad grade in your high school essay if you use ChatGPT, right? So this is not to say AI systems are not deployed in safety critical settings. I just have a few pictures in my slide about how it is. But the thing that to keep in mind is most of these cases, there are people the people who are working with these AI systems are specifically trained to work with these systems. They are in some sense trained to know the idiosyncrasies of the system. And even with these training, there are usually problems and stuff like that. We are far from a future where we can have a complex AI system like an assistive robot. Take it and drop it off in a remote village in India and expect an old person who knows nothing about AI or robotics to work, intuitively with the system. Okay, so this is kind of the goal here. Creating systems that can work and help with people as as if they were just another person. Okay, so how do we get here? So this is the question. Okay, so human-aware AI, or at least the human-aware AI agent architecture that I'll propose now, is my attempt at least what I think is a potential way of getting to that point. Okay, so this semester was my first time teaching an intro to AI course, and usually, if you are following one of Stuart Russell or like Peter Novick's textbook, this is how you start teaching AI. You start teaching AI by thinking of AI as an agent with actuators and sensors with potential models of the world. Okay. One of the other claims I'm going to make about AI in this talk is that this is the wrong way to look at AI. Okay. AI are intentional artifacts, any AI system. Okay, they're always built to work with people at some capacity. Even if you have a rover in Mars, there is some human who it has to interact with. So you can't just take the AI away from the human. There's always a human component that has to be taken into account. And I would say the way to look at AI is something like this. Whenever AI is making its decision, it doesn't have to just model the world, how its action would change the world and how it can get to the objective. It also has to take into account how its actions might affect the people around it, and what the expectations or beliefs that these people hold about that AI system. So this has to be part of AI systems reasoning about its action. And it needs to do all of this in a highly dynamic, complex setting. Okay, so this is like the long-term eventual hope and goal of my research. And of course, I'm not there yet. And this talk is in some sense my initial effort to get to this larger goal. This is more or less the slide that keeps me up at night and things like that. Okay, so where are we then? So let's do something simple to kind of, to address this problem. Let's take a step back. Let's look at a very, very simple setup. Okay, one where you have a human who's an observer, who's looking at an AI system just doing something. Okay, AI system has a goal. It has a model of the task. Hopefully all of you know what I mean by a model. A model is just like a formalization of what the agent, any agent, whether it's a human or AI, believes how the world would evolve with respect to its actions. So that's what I mean by a model. Okay, so AI system has a model about how the world works, what it can do and what it needs to do. Okay, and it has some reasoning process or algorithm that it uses with the model to come up with the actions or decisions it needs to do to get to the goal. Okay, and here the human is like I was saying, a passive observer. But even in this case, when a person is observing an AI system, they are, when previously before the talk started, we were talking about mental models, right? Theory of mind. People are ascribing certain beliefs to the system. They have some beliefs about what the system is capable of, okay? How what the system is trying to do, things like that, okay? That can in itself be captured as a model. And we as human have our reasoning capabilities, and we'll start forming beliefs about what the system will do. So the basic, one of the foundational problems or fundamental problems in this setting is what happens when the decision the system decided to follow, what the system decided it should do, doesn't match what the person expects the system to do. And this is the fundamental problem that we'll talk about today. And one of the claims I will again make is, if we want to imbue the system with two fundamental skills, okay, I would say these are two fundamental skills any AI assistant or any AI collaborator needs to have, namely explainability, that is the ability of these systems to justify or explain why it is performing certain action, and the ability of advisability, that is the ability to receive instructions and basically maybe advice from the human in a effective manner. These are two basic skills most AI collaborators would need. For the system to have these skills, they need to be able to address this asymmetry between what the human expects the AI system will do and what the AI system actually plans to do. Okay. Now, again, this asymmetry could be because of a lot of reasons and why there's a mismatch. So we will again make this problem simpler and focus on three very important dimensions of asymmetry. One is there could be difference in task knowledge, which is that what the human thinks about its task, what the human knows about what it's capable of, could be very different from what the human believes. Right? The human might not know about some skills the robot has, or a human might actually think the robot is more capable than it actually is. These are all knowledge asymmetries. Okay. Then there could be difference in inferential capabilities. There are a lot of AI algorithms like planning and RL algorithms that's able to solve very, very hard problems, which uses a lot of data that us as humans might have a hard time figuring out. So there is this difference in inferential capabilities. That would mean even if we had the same knowledge, we would have come up with different course of actions. Okay. Then there is the basic difference in vocabulary. The way the system is, capturing the world. It's, if you are using one of the, fancy new neural networks, it's all in terms of, vectors in huge high dimensional embedding spaces. People don't look at the world in those terms. People look at the world in terms of like high level concepts, in terms like objects and relationship between objects and things like that. So for the system to, in some sense, address this asymmetry, it also needs to be able to talk in terms that the human would understand. So this is what I'm talking about when I say there's a vocabulary asymmetry as well. Okay, so these are the asymmetry, and this is why there is a difference in expectation and what the system actually plans to do. Now, for the rest of the talk, I'm going to talk about the two skills we talked about, explainability and advisability. And I'll talk about how these skills connect to this asymmetry that we talked about, and how do we address them? How do we build systems that are able to, in some sense, be overcome this asymmetry? Then I'm going to talk about this larger idea of a symbolic middle layer, which can be thought of as a way to, at least one possible way that kind of connects all of them into a coherent framework. Okay, so let's start with the first part, which is the explainability part, which is the easiest like skills to connect to the system. Why do we need explainability? Because human thought AI system would do something, and the AI system is doing something else. So AI system has to explain why it's doing what it's doing instead of what the human expected it will do. And this is what I'm talking about when I say explainability, right? You're, in some sense, you're resolving this disagreement between expectation and what the system decided. And going back to our 3 dimensions of asymmetry, you can kind of see, the first 2 dimensions, the difference in knowledge and difference in inferential capabilities, giving rise to this difference in expectation. And then there is the difference in vocabulary, right? The fact that people don't look at the world in the same terms as the AI system shows one of the asymmetries it has to overcome to provide effective explanation. When it's explaining, it has to give it in terms people would understand. Okay, so I'll quickly go over some of my works that have tried to address these various pieces of these different dimensions of asymmetry. So the easiest one to talk about is the knowledge asymmetry, right? Like if we are saying the human might just not know some things that the AI agent knows, or human might have misunderstandings about what the AI agent is capable of and things like that. That means it might not understand, the human might come up with very different plans from what the AI system would come up with. And so there's a need for explanations there. And it might also seem like the easiest dimension to resolve, because all you need to do is, AI agents just need to give all the information it has to the human. Let's for now assume that there's no vocabulary mismatch. So AI agents speak in the same language as the human. So it just needs to give what it knows to the human, and things are resolved. Unfortunately, the issue isn't that simple. Usually, AI systems, the models that are being used by AI systems could be quite large, and there may be a lot of parts that the human might have confusion about, and a lot of them may not be, relevant to the problem at hand. So we kind of worked on this framework for explanation called model reconciliation, where we looked at, okay, starting from the human's model, what's the minimal amount of information that the system needs to get? Okay, so in some way, the system is giving information the person did not know before, and you're or maybe fixing some incorrect notions they have. But what are the minimal number of edits that you can do to get for them to correctly, understand the plan in question? So it becomes the search over possible models, where you're starting from the human model and you're trying to figure out what's the minimal number of changes you need to make. Obviously, one of the big assumptions being made here is the fact that you have this AI agent knows what the human knows, right? That's not always true. Some cases it's true, especially very structured settings, like urban search and rescue and things like that. Maybe the human and the robot start with the same map, and over time they just drift apart, right? So that's a case where AI system knows what the human knows, but this is not always true. So in the consecutive works, I've kind of worked on, in some ways relaxing this assumption. So the first relaxation I looked at was this idea of instead of having one model, we have a set of possible models. Okay, so I don't know the exact, the AI system does not know exactly what the human knows, but here are possible things that, here are possible background knowledges that the human might have. Can I come up with one explanation that would work for all of them? A good analogy to think about is something like a classroom. Think about a teacher coming up with a curriculum for students. They don't know exactly what all the students know, but they might have a set of possible students. Okay, here is a student who doesn't know anything. Here is a student who knows these bits and pieces, or those bits and pieces. Can I come up with a curriculum that would work for everyone, right? Something similar is being applied here. And then there was the case of, you have, the system has no knowledge about what the human knows. Can you still come up with explanation? So here you're looking for, here we basically made use of a learning-based method where we created this data set of how humans would react to different pieces of explanatory information, and try to learn a model of how humans beliefs would evolve in response to these explanations. Okay, so that was about the first dimension of explainability, and I kind of walked you guys through these like different works that started from a very structured setting and then relax it one bit at a time. That's usually how I like to work on these problems. And as you can see, we also started from a much simpler problem setting, right? Like look at the cleanest version of the problem, then try to make it more and more complex. Okay, now moving away from the first dimension and moving to the second dimension, which is this dimension of the differences in inferences capabilities. Here is a case where even if the human knew everything the robot knew, they would not have come up with the same decision. We are especially interested in settings where the problem is just too damn hard. It's just too complex that people can't make heads or tails of it. Okay, so how do we address this? So the way I've kind of gone around addressing this is I've used three main strategies. One is to allow for more interaction, like looking at ways people can ask more specific questions about these decisions. So they're looking at like, it's an interactive process. It's not a one-shot thing. You're asking more questions, you're getting more answers, and so on and so forth. The second strategy is what I would call model simplification, where for any given question that the human has, not the entirety of the problem is relevant. So you can simplify the model and give explanation with respect to the simpler model. Then there is this idea of explanatory witnesses, which is kind of like walking somebody through an example. Here is a simpler model. I'm going to walk you through the example and say why the argument I'm making holds true. Okay, so to kind of give you an example of a setting where all of these ideas were implemented, this was this paper which introduced this concept called HELM, which is like hierarchical expertise level modeling. So what do we do here is we take a complex problem, like in this case, a problem like, planning for extraplanetary rovers. These are extremely complex systems because they have a bunch of sensors, they have to do motion planning, they have to do scheduling, stuff like that, right? If a person were to ask a question, so here comes the interaction part, right? Asking a question, why didn't the robot go to that green cell? Okay, they're asking a specific question. For answering that question, most information about how the rover came up with its decision is irrelevant. You can, in some sense, abstract most of them, right? You're removing all of those irrelevant information from the model. Just talk about things like, oh, there are these obstacles, and I can't get to those things. Okay, and now to come up with the point of explanatory witness, you can now show them, if there is ways of simulating things, you can show them like a potential trajectory. If I were to follow this trajectory, here is how it will fail. So this kind of ties in all the possibilities. Okay, so there are other ways of course, simplifying things. It doesn't always just have to be like state aggregation based abstraction. There are other ways are like, you can break down the problem into simpler problems. So if you're talking about getting all the way to the green cell, you can talk about the sub problem of getting to this red cell first, and you can just talk about the separate. So there are a lot of ways of simplifying the model. Now, that was the second dimension. Now coming to the third dimension, this was the one we talked about, what if the AI system you're using is not reasoning about the world in the same terms that the human would. Okay, so to address this, one of the things we did was, AI system can use whatever model it needs to come up with its decisions, but based on the kind of questions the human asks, you can build post-hoc symbolic models. Okay, you can build symbolic models where the symbols correspond to things that human understand, and that this symbolic model has to, in some sense, parallel the true underlying model of the system. Okay, it doesn't have to be at the same level of fidelity. It doesn't have to be complete or anything, but we can create these simpler symbolic models as a post-hoc effort, and then use these symbolic models to provide information. So this was the way we kind of looked at explaining, as explaining in cases where there are these kind of vocabulary mismatches. And we specifically looked at the case of an ARM agent, which was basically learning how to perform things. So we looked at a problem like Montezuma's Revenge, where the system was learning by interacting with the black box simulator. Right? The Atari system can be thought of as a black box simulator, and usual state representations are not things that people can make sense of. But you can learn a symbolic model that kind of captures the dynamics of the game in terms that people understand, like, oh, here is the player is on top of this ladder and things like that. Okay, Sylvia, how are we doing with time? Okay.
We're good.
Great. Okay, so I'll go to the next step, which is the advisability aspect. Okay, so here the basic challenge is you want to be able to take instructions and advice from the human and provide this ability for the human to provide instructions and advice as they would to another user. Okay, why is this a challenging problem? So I would argue that this was the inverse and in many ways connected to the problem we talked about before. Because what's going on? In some sense, what's going on is the human has some mental model of the system, which could be potentially be wrong. Okay, they're using some kind of reasoning process to come about how the agent would act, and that could also be flawed. Okay, and then they are thinking about, oh, what instructions or what changes should I make to this mental model so I get the behavior I want? Because their mental model could be wrong, because their reasoning process could be wrong, and the fact that they're going to give these instructions in their language, all of these could be potential ways the system could misinterpret it, right? Because they might give an instruction thinking the system is capable of doing X when it is not. And if the system tried to directly implement their instruction, it could be an issue. This actually connects to a larger, more popular problem within AI safety called value alignment. You might have heard this, this term flying around a lot. It's currently used in a lot of sense, but I'm using it specifically in the sense it was introduced in the original paper which talked about value alignment. Namely, that the problem here is we actually have to ensure that the objectives or the instructions that the human specify will actually lead to behavior that the human expected in the first place and wouldn't actually lead to any unexpected behavior. Okay, so the popular problem here is the King Midas. Usually a story people use for value alignment is King Midas, the fable. That is, the king asks for a wish that whatever he touches turns to gold. But what he didn't realize, you can think about like it being a shortcoming of the reasoning process, is if you ask for that wish, you can no longer eat things, because whenever you try to touch your food, it turns into gold, right? So, and he touched his daughter turned into gold, and so on. So this is the idea. Like, you had some expectation when you made that wish, but it doesn't really match if that specific instruction or command is followed to the letter. It doesn't really match what your expectation is. So how do we kind of address this case? So my efforts in this direction has again been going back to, this asymmetry, right? So thinking about knowledge asymmetry, if a person is giving me a command, if I knew what their original mental model was, I can kind of form expectations on, okay, what they may have thought would be potential solutions to that particular, instruction or command. And I can see how close can I get to that instruction. If I cannot really achieve exactly what they expected, I can ask them questions about, is it okay if this happens or that happens? So there is an interaction process that's happening until I can ensure that the AI system can come up with a plan whose outcomes are going to exactly match what the humans expected. Okay, so that was this is all ongoing effort. So there is this an extended abstract for this paper in AAMAS this year that will be presented in like a few weeks. Then there is the question of a vocabulary mismatch. So this is again the inverse of the one we saw, where we were going from AI model to a symbolic model. Here, what we will do is humans command is turned into an incomplete symbolic model, and then we use that to come up with information that the AI system can use. And here, what we do is we take the symbolic instruction that the human gave and turn it into things like options or like some like high level, like temporally extended actions that the AI system can execute and so on. So actually, even here, there is, because it's a lossy process, there might be, there might be like uncertainty about how to exactly interpret what they are saying. So one of the ways we got around it is we are looking for like a diverse set of ways the human's instructions can be, in some sense, concretized, and then we try to make use of it in the underlying task. Okay, so this more or less brings us close to the end of the thing. So one of the idea that we've been kind of pushing, especially the previous lab, is one potential way we can bring all of this together into one unified system is to think of this idea of a symbolic middle layer. This is the symbolic middle layer you can think of as a symbolic model that is at a level of abstraction that is comfortable for the user, that is expressed in humans' vocabulary, that acts as an interface between the AI system and the human model, and the human and the AI system, right? So whenever human wants to give AI system some instruction, this symbolic middle layer gets updated, and then these updates are propagated back into the AI system. If there's a need for explanation, this symbolic model is used to come up with the explanation. The symbolic model could be updated if the current model is not sufficient to give correct explanation. So this, in some sense, ties together most of what we talked about earlier. Yeah, there has also been other recent work that I don't think we'll have time to go through. And one of them was like, can we give a mental model based account for trust? And I would say yes. And in some sense, it's very much tied to our expectations. When we say we trust someone, it's just basically that we expect them to, meet some goal, or like they're both capable and willing of achieving something. So that's what when we say trust, and it's directly connected to our mental models and expectations. Okay, so that brings us to the end of our talk. I want to thank all my collaborators, all my lab mates, and now all the students who agreed to work with me. And this is the end of the talk. So I'm thankful that my work has had some impact. And we also have a book that covers at least the first half of the talk about the explanation stuff. So yeah, I'll be happy to take any questions.
Hello, thank you so much for your talk. It was fabulous. We might need to connect offline later, but I'm doing research in a little bit similar area, and so I wanted to ask. I'm not sure how much overlap there is, but basically, I'm interested in trying to estimate the human's mental model live over time. And it's been a really difficult problem because as the human is learning about the robot, they have uncertainty. So like they're kind of trying on different models for the robot, or there's at least some sort of like uncertainty bounds on some fuzziness about their model. But then the robot is trying to estimate that, right? So the robot has uncertainty. So it's kind of been this curse of dimensionality situation. But I'm really intrigued how maybe some of this could really help with that, especially like you talked about explanations and advice or instructions. And I'm really interested how, if you have any like initial thoughts about how that exchange between the human and robot could also be information gathering actions, like that the robot could use to try to probe what the human's mental model is. I don't think you explicitly mentioned any of that. I also have not read your paper about the model-free stuff, which sounds most relevant, but any initial comments?
Yes. So in fact, there is a paper which was a follow-up on model-free explanation, and I can try to find the exact name. It was for user type. So we simplified the problem in some sense by assuming, okay, there's a set of users. The problem we ran into very fast is it's a POMDP. So obviously it's a computationally hard problem. And we looked at things like, oh, can we use online solvers like POMCP and stuff like that, and things like that. So clearly one of the questions is like the information gathering stuff. So there are some information in that paper, but I completely agree with your thing about, okay, you can ask questions about, okay, do you know about this, which would help you? So it doesn't just have to be about explanation. So there are multiple information gathering opportunities. One is letting the human react to your actions, right? So one is you behave and that's the human intervene. So when the human intervenes, you would get some information, okay, about, oh, okay, so this is a behavior that the human might not be okay with. But that's not always a great approach. Sometimes it is, especially if it's an offline process, right? Before execution. And there are cases where human might know things that the robot doesn't, right? So you don't want to execute stuff on the real world and find out, things blow up before the human understands. But there are many cases like decision support where it's an offline process. People are, working together to come up with a plan. So that's a case where these kind of probing strategies are very useful, right? You try out certain things because so more than the model-free paper, there's an earlier paper called the one where there are a set of models. One of the beautiful things you can do is even if you have uncertainty. So this lies at the heart of a lot of POMDP stuff. All POMDP solutions you can think of these two competing methods. One is the information gathering aspect, the other is the conformant aspect. Whereas even if there is uncertainty, maybe you can come up with a strategy that works for all the models. So there is this, balancing act you can think about. Even if you don't know exactly, everything the human knows, maybe there's a plan that that would be okay in all these uncertain models. So you want to reduce the space of uncertainty till you reach a point where you can do those kind of things, right? Where the remaining uncertainty is not as bad, that you can in some ways, live with that level of uncertainty. So you don't have to pinpoint all the way to a single model. Does that answer? I know it's all over the place, but feel free to reach out to me. Send me an email. My website is down below. I'll be happy to talk offline and give you all the links we talked about. Okay. Cool.
That sounds great. Yeah, and that's a great start. Thank you.
Yeah, and best of luck with your research. It's a hard problem, so I hope you have a lot of fun. Yeah,
thank you.
Especially the fact that it's a moving target, right? So that's something that has kept me up a lot. Yeah. Yeah.
Thank you.
Hi, Sarath. Excellent talk. I really liked your presentation. So I had a question about the knowledge part. So are you using I'm a bit confused here. So are you using some sort of a knowledge base or is it
yeah, go on.
Yeah, or for example, say what people usually refer to as, encoding common sense knowledge. Say, for example, you have a cup or a glass which contains liquid and you cannot pour that liquid into a box or those sort of things. So are you, is that something which you are addressing in this scenario or?
It's similar, but
okay.
I'm not going for the whole common sense as a knowledge base. Like we are not talking about knowledge graphs. I'm looking more domain specific knowledge.
Okay.
So
Okay.
a lot of my work looked at these things, at least models encoded in this language called PDDL, which is like
Okay.
planning domain definition languages. So they're
Okay.
looking for
Okay.
specific tasks at a specific level of abstraction. So that's the knowledge of it.
Okay. But can your technique be used to build such a knowledge base?
Yeah, yes. And people have looked at, parallel problems in the context of things like knowledge bases and stuff like that.
Okay.
There is still the same issue of, what human knows can be thought of as a knowledge base. There,
Yeah.
and then the AI system has a knowledge base. How do you
Yeah.
resolve this thing? So people have looked at, parallel works there.
Okay. Yeah. Okay. Thank you.
Yeah.
If there are no other questions, I will ask a question as well. So you talked about trying to find like a reasonable number of models that and find a solution and a strategy that could work for those, so that even in case of uncertainty, we can come out with something that works. I wonder, like, have you considered also trying to instead update those models in order for them to, like, you mentioned that as well in the book, like in order for them to learn something about each other, so that they end up aligned on certain aspects, then you can use in order to describe your strategy to, right? So I was wondering a bit more about, like, how would you use, basically it's the problem, the inverse problem about explainability for learning, right? For
So I touched on like parts, like different versions of the problem. I think the full problem is still I think it's a very interesting open question. So I looked at things like what's called as balance planning, where you're taking into account both explanation and then the plan. You'll say, okay, I'm going to give you this much information. After that, I can act the way I want. So you are anticipating what information I should give before acting. Right. So there is that question. The second, similar to the inverse thing is, what questions should I ask the person so I can do something that's going to be value aligned for him. So there's like some things I've started working on those lines, but I think the full problem is still open.
It's open.
Yeah.
And also, like, I think, like, when you ask a question as a robot, you would reveal something about what you know already. So even the human would update the model of the robot itself. So it would be asking the question itself would be already a way to make the alignment.
Exactly. So that's one of the big problem, the harder parts of this thing is this moving target thing that we were also talking earlier. The fact that, the human's mental model is not a single instance. It's actually something that moves along. Like it changes over time. So this, honestly, I think there hasn't been enough work done in the longitudinal aspects of these kind of explainability and stuff like that. And by longitudinal, I don't even mean an explanatory dialogue, but over time, when if you have something like an assistive robot, it's not a single task it'll do things over time and stuff like that. Things like trust. When we start talking about trust, it has to be about over time, over multiple interactions, because one way you can build trust is by showing competency, by showing that, oh, you can do it, and that's just showing them that I can do this or do that consistently. And so this question of longitudinal interaction, I think it's a big open question that I think there's a lot of work that has to be done there.
And what about approaches that integrate prior, like Bayesian inference, using this? Isn't it this like a feasible solution to take into account that the model is changing over time? The fact of considering a different prior, right? So you say, okay, now I'm going to take this bunch of data that are the last one I observed, and then my model would be this one, like my posteriors would be.
Exactly. So yeah, it's all, it's all compatible in this setting. So like the one I was talking about, the FORM-DP variation, that it in some sense it's keeping track of a distribution of beliefs over models, and it's updating its beliefs over time. So, but again, you can take the posterior from a specific interaction as the prior towards the next one, and then that becomes keeps going on over its interaction. Yeah.
Thanks a lot for your answers, and thanks for the doc once again. Yes. So our next session will be on the 7th of June, and what we are thinking is to have a more to try a different format for our talk, and to try to have a special session with in-person session. So we will be at ICRA for different reasons. So 2 of our group members will be there, and we will take this opportunity to talk with researchers there and come out with a podcast more than a video session or online session. So I invite everyone to stay tuned, and if you want to also, if you are at ICRA, to feel free to contact us if you want to speak about your research in this context.